So we're working now with 2 samples with hypothesis tests, and we have 3 different scenarios to run through. 2 independent samples with means. We'll look at a couple of examples of that. 2 independent samples with proportions, and 2 paired samples with means. And so the means is the harder one because we have to decide, are the 2 samples independent or are they paired together? So I'll give a few examples of each. So here we're going to take a look at an interesting study where people had to go to court for some reason, and they were given the option to smile or keep a neutral facial expression. And was the judge more lenient, depending on whether they're smiling or they had a neutral expression? So here we're going to test the claim that smiling rather than remaining neutral during a court proceeding will lead to a different punishment. So that is our hypothesis. And we need to figure out what is the null and the alternative based on that. We're going to have a sample of, in this case, 34 people who smiled during their hearing and 34 people who kept neutral expressions during their hearing. It says it's given below, but it's given on another page. Bear with me. And the values that are given measure how lenient the judges were. So let's take a quick look at that. So this data is available in StatKey. So we have a bunch of people who are smiling, and these are their leniency ratings on the punishment that was given to them. And then here's some people that had a neutral expression, and then their leniency rating is in the second column. Okay. So we got to figure out hypotheses here, and then we'll run our test. And we'll go run the test in StatKey. So let's see. Well, the claim above here is talking about different punishment. So we're measuring the average leniency. So let's define our variables first. So we have mu, let's say smiley people, which is the average leniency. Smiling people. And then we'll have a mu n, which will be the average leniency for people who better stay neutral. So in order to successfully run a hypothesis test, you got to know what your variables are and your hypotheses. So let's see, we have a claim up here that smiling rather than being neutral will lead to a different punishment. So that means they won't have the same leniency rating. So that says, the hypothesis above says the average leniency for smiling will be different, not equal to the average leniency of remaining neutral. Alternative to that would be mu s equals mu n. So in this case, we're saying there's no difference. If there's no difference, they're the same, right? Equal. And let's see, I'm going to squish this stuff up a little bit. Right here. Page 2. So again, we have one of our hypotheses that says the smiley people have a different average leniency than the neutral people. And so I'm going to subtract this mu n to the left. So another way to view this hypothesis is that the difference in their averages is, I wanted that to be the same, didn't I? N equals, the difference is 0. Okay? So 0 difference means they're the same. And then the other hypothesis was that they were different, not equal. So an alternate way to write that would be mu s minus mu n. So average leniency for smilers versus average leniency for people who remain neutral is not 0. So this is no different. And these are different. So which one's the null and which one's the alternative? Well, the null has to have an equals in it. Well, there's an equal, so that must be H0, null hypothesis, and this must be the alternative hypothesis. And the claim you're given isn't necessarily the null, and it isn't necessarily the alternative, it just depends which one has equals in it. So that's the hypothesis test we're going to run. That means it's a two-tailed test. All right, so that's the hard part. So again, deciding what your claim is, what your variables are, and what your hypotheses are. Once you do that, StatKey just takes over on the data. So let's let that happen here. Now, although I list the data here, StatKey has it already in there. So I'm just going to jump right to the data available in StatKey. And StatKey has a lot of data. Here's smiles versus leniency. Notice I'm at the randomization test for difference in mean. I need to be on the right page. And in this case, I have a lot of data to choose from, or I could edit and plug in my own data. That's another example. So StatKey automatically says, hey, your null hypothesis has to be that they have the same, that there's no difference. And notice that that puts a 0 difference in the bottom here for the scale. There's the data. I can see the smiling people have a slightly higher average leniency than the unsmiling people. Okay, so the Jeff was more lenient than the smilers than he was with neutral. But is that a significant difference? 0.79 is the difference in the two means right here. Sometimes 0.79 is a big deal, and sometimes it's not. Depends on the scenario. So to help figure that out, whether that's a significant difference, we have to run a hypothesis test. One way to run a hypothesis test is to make a sampling distribution using random simulations, which is what StatKey does. So I was actually given a significance level here. I was asked to test the claim using a 6% significance level, so the author here doesn't think smiling or not's a big deal in terms of leniency. We'll see. Well, the whole scenario is not a big deal. Maybe it is. Maybe if I smile, I won't have to pay a $200 fine. I'll only have to pay a $100 fine. So let's see. This is a two-tailed test. And I want a significance level of 6%. So for two-tail, I have to cut that in half, 3% in each tail. This would be the start of the picture I need to draw for this. And entering the significance level gives me my critical values here. So I should sketch that out. Picture time, always write down what these things mean, draw a picture. So I have my best symmetric distribution. In the middle is 0 difference, and StatKey for 3% in the right tail, I get 0.735 difference in leniency, or a leniency the other way, 75 on that side. That puts 3% of the samples in each tail. My data had a difference of color for that, X bar smilers minus X bar neutral people. That difference was 0.79. And if that's 0 and that's 0.73, then 0.79 should be somewhere over here. So that value right there is about 0.79. And so it looks like I'm going to have a smaller p-value. I have to find its symmetric partner over here, negative 0.79. These two blue areas together will be my p-value. So I have one piece of evidence already. And the first piece is that my test statistic is in the critical zone. And the next piece of evidence I want to collect is my p-value really smaller than the 6% significant level I was given? So let's go check that out with StatKey. So I just replace the right p-value, because mine's positive, 0.79. And StatKey gives me both the left and right percentages added together give me 0.044. So that's my p-value here. So my p-value of n is not a function. There we go. My p-value is approximately 0.044. My alpha, by the way, remember, was 0.066%, and so my p-value is definitely less than alpha. So since it's in the critical region and the p-value is less than 0, then I get to reject the null hypothesis. Everywhere there, and which means my data gives me evidence that the alternative is correct, that there is a difference. So as far as my conclusion goes, my conclusion is going to come from the written description of the hypothesis that the data supports smiling rather than remaining neutral during a court proceeding will lead to a different punishment from the judge. In this case, we think it's a more lenient punishment than a more severe one. All right, here's a different example. Let's see, you are testing the claim that having lights on at night increases weight gain. Interesting. A sample of 10 mice lived in an environment with bright light on all of the time, and 8 mice who lived in an environment with normal light-dark cycles, and it's given below. Below is back here. So this is the average weight gain of the mice that lived in the bright area versus the ones that lived in the dark area. And in my open math, I have a link to an abstract about this study if you want to check that out. So what are our hypotheses? What are our variables? That's the big question. So let's see. We have 2 different groups of mice. So if they're not the same mice, this should be independent, I think. Safe bet sometimes, as opposed to if they're matched. So what's an example if they're matched or paired? Well, suppose instead we were looking at couples, husband and wives, and their age. Well, they would be matched or paired because they are married. And we're looking at the ages of each of them, say, and we want to find out if the husband has a different age than the wife. So that would not be independent, and hence this would not be the right kind of test to do. So we'll do one like that next. So I'm not going to go through the whole hypothesis, but I just want to write my variables down and get it started. So let's see. We have a pen. There we go. I need a new pen. Mu of the light mice. So this would be average weight gain for mice in always lit environments. Spell that. And then let's say we have mu dark mice, and that would be their average weight gain. Again, this would be for the mice in your normal light-dark cycle. And we want to test the claim that having the lights on increases the weight gain. So that means mu for the light mice should be greater than mu for the dark mice. Okay? Test the claim that increases the weight gain. So we'll have more of an average weight gain here. Since this is just a greater than, an increase would be a greater than, This must be the alternative hypothesis, A. Another way to state the alternative hypothesis here would be that mu light minus is minus, back that onto the other side, and it's mu dark minus, so the difference in their averages light minus dark is greater than 0. And often, instead of calling them mu light and mu dark, you might see notation like mu 1 and mu 2. And that's the order the data is presented. And in this case, let's double check that that was true. Yeah, light mice is presented first. This data is available in StatKey. And we just have to switch from smiling to, and I think I recommended weight gain second edition. And the light is given first because it's at the bottom of the chart over here on the original sample. Looks like the average difference light minus dark was 2.62. And the table gives the light data first and the dark data second. So something to keep in mind, if you do want to use a difference in means for independent samples in StatKey, if you paste data in, it has to be in this format here, where you have a label for each quantity. And there's 2 labels, 2 different groups. All right, so again, the hard part there, or the first hard part, was deciding what the hypotheses were. And so we're going to do a light is greater than dark. We're going to do a right tail test on that. All right, so let's look at another one. Here we're going to test the claim that a male's self-reported height is different from his actual height. Well, who cares if somebody says they're taller than they really are, right? Well, it turns out it could matter. So several studies have been done in this. And let's say a person says they're taller than they are, but if you ask their weight, they're probably going to say they're lighter than they are. That's pretty typical. If you put the 2 of those facts together, there's a measurement for obesity that takes a ratio of height to weight. And if the height is too high and the weight is too low, the person will appear smaller on the obesity scale. So what that means is if you did a study where people self-reported their height and their weight and you tried to calculate their obesity, you would find there's less people that are obese in the population than there really are. And that is a problem for trying to deal with health issues in the region. So this is a big deal, although we're only testing it with a 5% claim. Let's take a look at the data. Oops, button. Oh, that's not the one. Sure, I have this here somewhere. This. Oh, I remember. 10. There we go. In this case, because the data values the height that's self-proclaimed and the clinical height, they're connected, right? They're matched to the same person. I can't use the difference in means test through StatKey. Instead, what I have to do is calculate all the differences first. So I don't actually need the height they said they were and the height they actually are. What I need is the difference in height. And so I have a bunch of measurements here. These are given in centimeters. So somebody didn't think they were 7 centimeters taller than they were. They thought they were 7 inches. They thought they were 7 centimeters taller. So I need the difference to make this happen here. So for StatKey, I'm not going to go to the difference of means page because this is only if the samples are independent. These are not independent because they're from the same person, each of these numbers. I have to go to the test for a single mean. Do that one right there. All right, so let's move on. And again, you would just have to copy and paste that data in the StatKey. So I guess we should check that for fun. Sorry about that. All right, so copy, Control C, move over to StatKey. And again, I'm on the randomization for a single mean. I'm looking at the mean of a difference, and I would have to edit that data and drop in here. When I copied it, I didn't copy the header. So I then hit OK. And then it looks at the difference here for me. Now, one problem here is in the independent samples, I'm automatically given that they're the same or they have a difference of 0. In StatKey, for the difference into paired means, I have to go again to test for a single mean, and then I would set the null hypothesis to 0, meaning there is no difference in heights. So for this one right here, I would have for hypotheses that for the null, mu for the self is equal to mu for the clinical measurements. The alternative version of that is that your mu self, let's just call it mu s, minus mu clinical 0. Right, so I had to set that null hypothesis in StatKey. The alternative hypothesis here would be that, let's see, is different, so that would be not equal. That could also be written as mu self minus mu clinical is 0. All right, another example. So what else do we have? Okay, GPA. So this is one that's not in StatKey. So we want to test the claim that the mean GPA of night students is different than day students. So is this paired or is this independent? Well, if you're a night student, then you're not a day student. If you're a day student, you're not a night student. These aren't the same person, but they are independent. So this is 2 independent means. The null hypothesis would be that mu night is given first is equal to mu day, that they're the same. The alternative is given here, that mu night is not equal to day. To use this in StatKey, since it's not already there, the data has to be in the right format. So somewhere here I had that one, this one, yeah. So here I give a table of night, and notice it's night value, then day value, day value. So to copy and paste this in, I would highlight first one table of data. And some browsers this doesn't work so well in. Found that edge can be a problem. And this is a test for a difference in means because they are independent. I can just edit the data, get rid of whatever data is in StatKey, paste in line, enter for a new line, and then go grab the other group of numbers. This one, paste those underneath. And again, notice I didn't copy the header, so I definitely want to uncheck that. Otherwise, it'll block out that top number as labels. Okay. So it says the average of the night students is 3.275, average GPA of the day students is 3.165, for a difference, average night minus average day, of 0.12 in their GPA. And then you can go run your hypothesis test. So once I get the data in there, it's no different from running hypothesis tests in single means and single proportions like we did before. A matter of running it, seeing if your value is in the critical region, and then making your decision whether it is or not. All right, last one. Let's take a look at test the claim that the proportion of men who own cats is smaller than the proportion of women who own cats. Significance level is 2.5%. So I have a similar problem over here somewhere. Go. So what do we got here then? We have to come up with our variables. So this is a proportion, not a mean. So that means I would go to the difference in proportions page. I have to decide what kind of test this is, a left tail, right tail, two tail. In this case, I have proportion of men is smaller than proportion of women. That has to be the alternative because it has a less than and a proportion. So let's see, men is greater than females, not equal. That's a mean, that's out. That's a mean, that's out. Proportion less than would have to be this one right here. Null would be proportion of males is the same as the proportion of females. Alternative is the proportion of males is less than the proportion of females. That means it is a left tail test. And then they give me the data. So of 40 men, 40% of them own cats. So now it's time to go to Statistic. So up here I have a link to a test for a difference in proportions. And I want to edit the data. So the sample size was 40, and 40% of them, so 40% of 40 should be 16. The women, we had 60 women and 60% of them own cats. So 60 is the sample size, and on a good day, 60% of 60 is 36. So enter your counts and your sample sizes. Okay, and then check to see if Statistic did it right. So 40% of group 1 is my men, 60% of group 2 is my females. Got it. So I have a difference in proportions of negative 0.2. So they're 20% difference. There's more females who like cats than males. So this is my test statistic right here that we'll use in a moment. So once that's in there and I have my hypothesis set, which Statistic sets for me on a difference, I generate many samples. Remember, we're building a sampling distribution. So each one of these is a different sample of 40 men and 60 women that have slightly different tastes on cats. So there's the distribution. I wanted a 2.5% significance level. It is a left tail test, and Statistic gives me that right there. Ooh, this is trouble. So one problem I have here is that my cutoff value is exactly the same as my proportion, and that is not supposed to happen in reality, but it does sometimes when we roll the dice. So I'm going to set box. Oh, it doesn't happen again. Let's try this again. Left tail. Ooh, damn, it happened again. Okay. So that means I have a crapshoot here. Is it more significant or not? Or not? It matches. So my test statistic is the difference in the two proportions. 40% minus 60% is 20%. The critical value related to that, well, according to Statistic, that's also negative 0.2 when I entered my confidence level. So that significance level, yeah, 2.5%. Okay, so do we reject or fail to reject? Since they're equal and one isn't specifically less or greater than the other, I'm going to fail to reject here. Hope I got it right. Chance I'm going to get it wrong. Submit. Ooh, I got everything right but that conclusion there. So in theory, it must have gone the other way. Yeah, so that's a weird case that happens with simulations sometimes where the things match exactly. Shouldn't happen very often, so hopefully it won't happen to you. All right, that's it for now. Call or write or stop by if you have any questions. We get hypothesis testing. Bye-bye.